Okay, YouTube, in this video we're going to talk about if we are given functions, say some function of x, how we can apply different transformations to it and how it would necessarily affect the graph so that we can come up with quick sketches of graphs given our knowledge of basic transformations, okay? So the very first set of transformations we're going to talk about here are vertical and horizontal shifts by some constant c here. And we say shifting graphs c units upward or c units downward, I'm basically going to say that the way we would necessarily accomplish this is f of x plus c or f of x minus c, where c is some constant. Now recall that our f values, our function values, are really the same thing as our y values here. So what would happen to a function if you took all of its original y values and added some constant to it? So what I've got is this tool over here where I say enter a function for f of x and select different transformations on the left over here. Essentially what we're going to do is this. I'm going to choose a function here. Let's go with, say, our squared function. F of x equals x squared. And you'll notice that I have all these options over here. And our first set of transformations is this right here. We say f of x plus c. Now, I didn't write a minus c here because I'm going to allow c to assume different values. But I'll click on this to highlight that. And you'll notice that we get the same function right here because right now f of x plus c is f of x plus 0. So in other words, f of x plus c is the same thing as our original x squared function. But what I want everybody to see is this. If we were to take all those f of x values and add 1 to them, those y values, you'll notice that basically all of our values on the original graph were just translated up 1 unit. And even better, I mean, we could even type in f of x plus c here, and you can see that all of these values basically just had 1 added on to them. So when we add or subtract some value off of or onto the function values, the y values, all we're really doing then is translating our graph or shifting our graph up or down c units. So that's the very first thing we want to acknowledge here. F of x plus c or f of x minus c is going to shift our graph c units up or down. Now, to shift our graph left or right, what we're going to do is a little bit different. We're going to say it's f of x plus c or f of x minus c. Okay, you'll notice that our constant value that we're adding on or subtracting off in here is on the inside of this. And as a matter of fact, I do need to switch this around. We'll kind of talk about why here in a second. But you notice that I write f of x minus c. It's really important that that actually shifts it to the right. Whereas before, if I were to put positive c, you would naturally think it shifts it up, or negative c, it shifts it down. When we write f of x minus c, it actually shifts it to the right. And to shift it to the left, it's f of x plus some constant, assuming the c is some positive value here. So again, I would like to pop over here and say, well, with our quadratic function here, instead of doing f of x plus c, where c is some constant, what I'm going to do is I'm going to do this f of x plus c here, and I want you to see something here, no pun intended, but as I move our c to more positive values, that is, if I have a plus c in here, our graph actually translates to the left, and to the left exactly that many units. So for instance here, the value of c is positive 2. If I were to write f of x plus 2, our original graph actually just shifts left 2 and then just goes up 1, right 1, and has the same basic shape of a quadratic function here. Whereas if I were to make it negative, it actually shifts to the right, okay? And it shifts to the right exactly c units, all right? So I'm going to get rid of that transformation there, and we'll go back over here, and we say, okay, it's very much the case that if you were to add in this constant inside of your input value, and not to just the y values, but to the x values, you're shifting your graph left and right. Okay, so let's talk about our reflections here. If we want to reflect something over the x-axis, I mean, thinking about this function right here, what could I do to all of the y values of this function here that are going to make them open downward or shift it over the x-axis? And the thing is, we wouldn't change the x values. The x values would stay the same, but what we could do is we could really just say, well, what if I were to take our y values and make them all negative, like negative f of x values? And you can see that it would just pop over this graph here. So really what I want to do is I'm going to go down here to this transformation where we say if you make all the y values negative, if you make the function negative, it actually flips over the x-axis. So to make your y values negative, flips it over the x-axis, okay? What would happen if we made all of our x values negative? Now the interesting thing is that would be f of negative x, if we plugged in negative x values. I'm going to click on this here, and you notice that I have two graphs showing up on top of one another, and the reason why is because when you make the x values negative, it reflects over the y-axis, and this graph actually, since it's an even function, reflects onto itself. So say, for instance, I were to go up here, and we'll make this an x cubed graph, a cubic graph. Notice that I have my regular function here. If we do f of negative x, or make all of our x values negative, then it actually reflects over the y-axis, okay? If we were to make all our y values negative, then it pops over the x-axis, okay? So in terms of reflections, we just want to be really clear on the fact that if you want a reflection in the x-axis, we're really looking to make all of our y values negative. And if you want a reflection in the y-axis, we're going to take all of our x values and make them the opposite of what they were. Okay. So now for our last kind of exploration here, we talk about non-rigid transformations. And by rigid transformations, these are all over here, these are rigid. The reason why is because it preserves the shape of the graph. The shape stays the same. Okay. What we're going to do is we're going to perform non-rigid transformations. We say shifts and reflections are rigid because they preserve the shape. But when we talk about vertical stretch and horizontal stretch, or maybe even shrink, we're talking about a situation where perhaps we're taking some constant times the y values. What would happen if you took all the y values on a graph and you doubled them? Okay, so we would get some vertical stretch, okay, where our y values would extend even further away from the x-axis. So we say that we'll get vertical stretch if and only if we're multiplying all of our y values by a number bigger than 1. But what happens if you multiply them by a proper fraction, okay, where the bottom of the fraction is bigger than the top, but it's actually still positive, okay? Then we'd say that some number times f of x where it's a proper fraction would cause vertical shrink. So what we're going to do is we're going to play around with this notion here. If I were to take now our f of x here, and I say, okay, well, let's do this. Let's graph a, or we'll do c. C times all of our y values on this function right here. Right now, c is equal to 0. So what's going to happen if you take all these y values and you take them times 0? They collapse to 0, and you notice we get this straight line. But the moment that we make c some number between 0 and 1, you notice here that the function x values stay the same, but it's shrinking down to the x-axis. And if we were to make c have a value bigger than 1, it actually starts to stretch by that factor there. So if we make c equal to 2, instead of starting at the origin and going through 1, 1, it'll start at the origin and it'll go through 1, 2. Okay? Everything in terms of an output was essentially doubled. So it's important to know that when you take all the y values times some factor bigger than 1, we're going to get a vertical stretch. And if you take all the y values times some factor that is a proper fraction, we get vertical shrink. So now the question becomes, what if we were to apply this multiplication of values to the x values and not the y values? We will get horizontal stretch, and this is kind of backwards from shrink, if you were to multiply it by a proper fraction, some number between and not including 0 and 1. So to apply this stretch, we multiply the x value by the reciprocal of c. Okay, you multiply the x value by the reciprocal of c if you have vertical stretch. So essentially, we would multiply it by 1 over c. Multiply the x values, multiply x values by 1 over c. Okay. Whereas if we have horizontal shrink, that is, we're multiplying all the x values by some c, where c is bigger than 1, it says to apply this shrink, multiply the x values by the reciprocal of c. Okay. So we're going to do that there. And I think this is cut off here, but we'll kind of look at some examples where this happens. So instead of looking at that transformation, basically what I want to do is I want to look at some applications of transformations. We say apply transformations. The interesting thing here is we're usually going to be dealing with some defined f of x value, but what I'm saying is in this case, f of x is just this function right here. And in all of these windows, you notice that f of x is the same in all of them. So given some f of x, what's going to happen to our function if, say, we add a constant to all the y values? So looking back at what we wrote down over here, we say, well, if I were to add a constant to all of the y values, what's going to happen is we're going to have some vertical shift, either c units up or c units down. So really, to take some new function here, we could say like g of x, and say it's really the original function plus 2 to all the y values. Really what's going to happen is all these y values are going to shift up twice. So we can pick up each individual point and shift each individual point that's given here up twice, and you get this right here. And connecting the dots, what we can see is we get this new function that was just translated up 2 units, okay? Now looking at this transformation, this is kind of an important thing, but remember, when we're dealing with some value that's added onto or subtracted off of the x value, it's kind of backwards, okay? That is to say that if we were to take 2 away from all the x values, what really happens is it shifts left and right, but specifically to the right, okay? So it shifts right 2 units. In the same way we did the last one, we're going to do this one. We're just going to grab all of the individual points that are clearly defined, and we're going to shift them right 2 units. and we can just draw in this relation again here. So we see this rigid transformation where we actually shifted it right to or translated it right to. Let's take a look at these here. We say now I have a new function y that's equal to 2 times our original function. Keep in mind that f of x are our y values. So if you double your y values, what we're going to get is some vertical stretch. We're going to get vertical stretch, and I'm going to say by a factor of 2. So what we want to realize here is we're going to take all these original y values and we're going to double them, okay? That is to say, if this is at a height of -1, this is 0, -1, we're going to get some new point now that is at 0, -2. So this stretches away from the x-axis. Interesting thing here is since this was at a height of 0, well, if you double 0, it's still at a height of 0. If we were to double this height here, well, it's at a height of 1 now, so now it's going to be at a height of 2. And previously, this was at a height of 2, so now it's going to be twice as far away from the x-axis. So we're going to double the y values here. And we get this right here where we have some transformed version of this function where we have vertical stretch by a factor of, and I forgot to write 2. Next, we see this. We say I have a new function, and all it's really equal to is the original function where we make all the y values opposite. So what we see here is we're going to have a reflection, and since we made the y values opposite, we have reflection over the x-axis, okay? So we're really going to take all the y values and we're going to reflect them over this imaginary line on the x-axis. So our new function, instead of being 1 below here, is going to be a 1 above. What if you were to reflect a point that's already on the x-axis? Well, it's going to stay on the x-axis. This will reflect over to here. And we have this at a height of 2, now it'll be a height of -2. But basically all we really did was we reflected this over the x-axis. So let's go ahead and take a look at just a couple more transformations here. I got them hiding right there. If we were to take f of x plus 3, now again, we were adding or subtracting onto the x values, which is going to cause horizontal shift. But because horizontal shift is backwards, this is going to shift left 3 units. So grabbing all of these here, we'll go left 1, 2, 3. Take the x value, move it left 3, move this one left 3, move this one left 3, and so we get this here. And then now notice on this one we're making the x values negative. So whenever you make the x values negative, we're going to get a reflection, and it actually reflects over the y-axis. So since this has an x value of 0, well, make 0 negative, it stays the same. This one has an x value of 1. If we reflect it over the y-axis, it's actually going to go to -1. This has an x value of 3. This will go to -3. This one has an x value of 4, so this one will reflect over to -4. So here's our reflection over the y-axis. And then last but not least, this one here. Now this is interesting. We're not multiplying all the y values by a given value. What we're actually doing is we're multiplying all the x values by this given value. So what we're going to do is we're going to take, I'm going to write this here, horizontal. And since this is a number between 0 and 1, it's actually going to be stretch. It's backwards from vertical stretch, where you have to multiply all the y values bigger than 1 to get a stretch. When you multiply x values by a number between 0 and 1, you actually get horizontal stretch. So we're going to get horizontal stretch by a factor of the reciprocal of 1/2. So we say by a factor of 2. And really we could say multiply the x values by 2. So if we were to double these x values now, again, this has an x value of 0, so the new function, the transformation, is going to stay at that. But we said this has an x value of 1, now it's going to be stretched by a factor of 2. This has an x value of 3, well, now it's going to be stretched by a factor and 2, and it's going to be out at 6. This has an x value of 4, so it's going to be out at 8, and it would look like this. So these are our essential transformations. In the next video, we'll talk about how we can use those basic transformations to rewrite a function and quickly sketch its graph. Cheers.